Thank you for introduction. I'm Kaori from Yahoo, Japan. This work is part of my PhD thesis and mainly conducted during the internship at Microsoft Research. In this talk, I'd like to introduce Ohmic-Sticker, pasteable, thin, and passive attachment for capacitive touch surfaces. A TrackPoint is a stick-type pointing device providing forced motion input. It was proposed by Masaaki in 1990. Recently, a TrackPoint is difficult to find on modern laptop PCs. Possible reasons are mainly in assembling. Because of the thickness of the structure, it is difficult to adopt modern thin devices. Even with the sensor versions of ThinkPad, it still requires thicker structure. Also, TrackPoint is kind of old technology. However, as you can see, there are many attempts to add a TrackPoint to DIY keyboard or casing or laptops. This is because TrackPoint has some attractive features, such as its small footprint, using small finger movements, and no clutching actions needed for continuous input, such as scrolling or dragging. We also considered it will be a promising add-on option if a forced motion pointing device can be easily attached to the existing hardware. Hopefully, hardware teardown. We focused on the touch surfaces because most of modern laptops have it. Researchers have developed attachments for touch surfaces that provide forced motion input. Ravage provides combination of conventional touch interactions and force-sensitive inputs on the edge of touchpad. One application of the flexible realized stick-type pointing device. Because of the capacitive sensor made of 3D printed conductive material, it requires a bigger or thicker structure to realize sufficient change in capacitance. And CAM TrackPoint also provides forced motion operations. Since it uses images from camera to sense finger movements, it is difficult to adopt laptop PCs. Here, we propose Ohmic-Sticker, a novel forced motion input device. Ohmic-Sticker works simply by attaching to the touch surface, and it enables passive and thin form factors. A force vector applied on the structure can be detected as a shunt current from the corresponding touch surface electrodes. According to the pattern of comb electrodes, it realizes various force-sensitive interactions. And this pattern enables 0.5 of operations. By dividing the comb electrode into 4 areas, it can provide 2.5 of operations. Here, based on this simple pattern, I'll describe the basic structure of Ohmic-Sticker. Ohmic-Sticker has a force-sensitive resistor on the PCB. It changes its resistance value according to the applied force. This is a fabrication process. The force-sensitive resistor consists of 2-layered PCB, double-sided tape, conductive film, and rubber cap. The double-sided tape acts as a spacer. When the external force is applied to the film, the contact area between the film and the electrode is changed. Thus, resulting in a change in resistance value from 100 megaohms to tens of ohms. The FSR-based structure realizes a significant change in resistance value while retaining their thin structures. It is difficult to realize in the case of using capacitor. One end of Ohmic-Sticker is connected to a touch surface, and the opposite end is connected to the ground. To detect the change in resistance value, we used Ohmic-Touch technology, which we previously proposed. Originally, the software measures shunt current for the internal electrodes, and it changes depending on the impedance of the passive touch. In Ohmic-Touch, various interaction can be provided by using the change in resistance value of the inserted object. Similar to the Ohmic-Touch, the force vector applied on the Ohmic-Sticker can be detected as a shunt current for the corresponding electrodes, and thus force-sensitive analog inputs can be realized. Here, I would like to explain the investigations for the design requirements of Ohmic-Sticker. For the implementation of Ohmic-Sticker, there are two options for ground connection. One is using human body, similar to the Ohmic-Touch. And another one is device ground. In this method, connecting the ground via the device casing. In general, circuit boards inside the surface are electrically connected to the device casing. So, the casing can be used as ground. Both the connection methods have pros and cons. Firstly, in the human body ground, the ground condition of the user might affect shunt current measurement. This effect will not occur in the device ground. So we tested the stability of shunt current measurement with each connection method. In this experiment, we use a touchpad-like apparatus that can switch between both connection methods. We selected the combination of ground conditions. Firstly, touching or non-touching between the user's body and casing. Second, using AC adapter or battery pad conditions. With this, we recorded the shunt current. It shows the main shunt current for each ground condition in the human body ground. The shunt current was stable in AC condition, but it fluctuated in the battery pad condition. In contrast, as we expected, the device ground was stable for all conditions. So we selected the device ground. By the way, how about non-metal casing, such like plastic? Yeah, no problem. The device ground could also be adapted for non-metal casing because the inside of casing is shielded. Next, regarding the device ground, although it enables stable shunt current measurement, we have to consider the effect of adaptive filtering. Most of the test softwares have adaptive filtering function. The purpose of filtering is to discriminate stationary inputs from finger touches. Similar to this, touch inputs by Ohmic-Sticker is also detected and then disappear after a short while. This is because a certain value of the current continuously leaks to the ground. The force sensor used in Ohmic-Sticker maintains a certain resistance value without applying pressure force. We call this value as zero force impedance. We considered the touches detectable or not will be determined depending on the zero force impedance. So, we check the filtering behavior with various zero force impedance. It shows the result of change in shunt current. In either condition, the measured shunt current decreases with time, and finally ceases to be detected. After the filtering, we decrease the resistance value of the apparatus. The shunt current increased when the resistance value was decreased, thereby cancelling the adaptive filtering. But in the case of lower than 30 kiloohms, the amount of background shunt current was already too high, and the filtering was not cancelled. So we confirmed except when the zero-force impedance is too low. The shunt current is detectable even after the filtering is activated. Based on the investigations, the design requirements for Ohmic-Sticker are determined such as this: using device current method and setting the appropriate zero-force impedance. Now, we realize force-to-shunt current structure. The next step is to realize force-to-motion. The mapping between the force and causal speed. Here, I'd like to explain the implementation of Ohmic-Sticker to imitate the TrackPoint operations. To implement a software that provides TrackPoint-like force-to-speed function, we firstly investigated the mapping between the force and shunt current of Ohmic-Sticker. And second, we checked the force and causal speed of TrackPoint. Finally, we derived the mapping between the force and causal speed for Ohmic-Sticker. This is a quick summary of derived force-to-speed function for Ohmic-Sticker. Owing to the differences in detectable force range between TrackPoint and Ohmic-Sticker, we modified the original transfer function. For the details, please see our paper. Then, by using the Ohmic-Sticker with the implemented force-to-speed function, we evaluated its performance. We conducted an experiment involving a traditional pointing desk for Itiro. We compared the Ohmic-Sticker to commercial TrackPoints. It shows a result of performance for each device. We confirmed both device conditions exhibit good fit to Itiro, and the mean throughput of Ohmic-Sticker was 79% of TrackPoint. A possible reason for lower throughput is in the force-to-speed function. The actual implementation of the TrackPoint driver includes a raised dynamic pointing function and many heuristics that have been accumulated since Tetsuya proposed the initial TrackPoint. Our implementation doesn't fully imitate the TrackPoint driver, so there's room for improvement. Here, I'd like to envision a number of applications. The 2.5 Ohmic-Sticker can provide TrackPoint-like operations. And note that the remaining area of the touch surface can be used for conventional touch interactions. The 6 Ohmic-Sticker allows the user to navigate a 3D space smoothly. In addition to 6 operations, scrolling and zooming can be realized by pressing to the both pointing heads simultaneously. Ohmic-Sticker is also compatible with smartphone. In this example, it provides backup device interaction for 100 operations. For that implementation, we use capacitive raw images from kernel-hacked Android. It can also be used for cardboard HMD. It enables for operating the smartphone from outside of the HMD. It is also adaptable for tabletops. It allows the user to operate with a small finger movement even on large surfaces. This is an easy setup for game controller for standard type touchpad. It is also adaptable for smartphones or game devices having touch panel. Here, I will discuss the interference with the existing form factors. Ohmic-Sticker occupies a part of touch surface. In the case of using 2.5 or MacBook, 60% of the input area will be occupied. Thus, 84% of the remaining area is still available for conventional inputs. Regarding the attaching position, typically TrackPoint is embedded between the Z, H, and B keys on the keyboard. It is difficult to attach Ohmic-Sticker at the position. However, attaching it below the space key is possible. And next, regarding the thickness. Also, the thickness of Ohmic-Sticker is less than 2 mm. It's very thin, but it is considered to interfere with the screen when closing laptop. Adjusting cushioning with the same thickness can prevent such interference. Finally, regarding the potential force activation, such as when user accidentally touches the electrode on Ohmic-Sticker. In this case, the shunt current will rise much faster than the pressing on the pointing head. So, using the differences in the rising speeds, force activation can be avoided. Let me conclude. We propose Ohmic-Sticker, force motion type input device that realize passive and thin form factors. Finally, today I have one Ohmic-Sticker is attached to my laptop. If you're interested in it, please talk to me after the session. Thank you.
All right, so we have time for a few questions. All right, I'll get the ball rolling. So you talked a bit about the size of the tag, like you showed that on the with the plastic casing of the laptop, a slightly bigger tag would have helped. Can you talk a bit more about how the size of the tag will affect performance in general?
Okay. The sensitivity of force motion input is mainly affected